Yes, so we are about to start the final talk for today by Albert Kubzdela, and the title is Finite Dimensional Decomposition Property for Non-Archimedean Banach Spaces.
So I can start. Yes?
Yes, yeah.
So thank you for the opportunity to participate in this conference, and this way the opportunity to meet old friends. I'd like to present the talk, the finite dimensional decomposition property for non-Archimedean Banach spaces. Short outline. First, I'd like to present a short overview of classical results. It means results for real Banach spaces. Next, going to the non-Archimedean world, I'd like to characterize the concept of the orthogonal finite dimensional decomposition property and present its selected properties. Most of the results are obtained jointly with Cristina Perez-Garcia, supplemented by a brief overview of results obtained by Cristina Perez-Garcia jointly with Wim Schikov concerning metric approximation property. By the way, recently I have contacted with Cristina Perez-Garcia and said her about the planet talk, and she asked me for transmission greetings from her to p-Adics colleagues. So, cordial greetings from Cristina Perez-Garcia. As I announced, I start with the short overview of classical results. So the story begins in 1927 when Julius Schauder introduced the concept of topological base, later known as a Schauder basis. And it's defined as a sequence in X is called a Schauder basis of X if for every X there is a unique sequence of scalars, the coordinates of X, such that X can be expressed as follows. Some generalization of this notion is the concept of the Schauder decomposition, which was introduced in the mid-20th century, and a sequence of non-trivial linear subspaces of a Banach space X is called a Schauder decomposition of X if for each X there is a unique sequence, such that every element belongs to the proper matter of the sequence, such that X can be expressed and associated orthogonal projections are continuous. A Schauder basis decomposes a Banach space into a direct sum of one-dimensional subspaces. Hence, every Banach space with a Schauder basis has a Schauder decomposition. But not every Banach space has a Schauder decomposition. And for example, L infinity has no Schauder decomposition. Also, among separable Banach spaces, there are examples of Banach spaces with no Schauder decomposition. For instance, a linear subspace of the space of Hubert and Morey, constructed by these two authors. Hence, a Schauder decomposition appears as a generalization of the concept of the Schauder basis. A Schauder basis decomposes a Banach space into a direct sum of one-dimensional subspaces. And it's quite natural to study special type of decomposition, namely finite dimensional decomposition, which are defined as follows. The sequence of finite dimensional subspaces of a Banach space is called a finite dimensional decomposition for X if there is a unique sequence such that X can be expressed as limes of the series, and we say that the Banach space with a finite dimensional decomposition has the finite dimensional decomposition property. Clearly, every Banach space with a Schauder basis has the finite dimensional decomposition property, but the converse is not true. There is known several examples. One of them is the example of Sharek, of separable Banach spaces with finite dimensional decomposition which fails to have a basis. Now it's time to start the non-Archimedean part. First, well-known notation and concepts. From now on, K denotes a non-trivial non-Archimedean valued field, complete with the metric induced by a non-Archimedean valuation. I mean that a non-Archimedean valuation is a map defined on K with values in non-negative reals such that three conditions are satisfied. We say that K is spherically complete if every nested sequence of balls in K has a non-empty intersection. Otherwise, we will say that K is non-spherically complete. In addition, two examples. For the first class, the field of p-Adic numbers is an example of spherically complete valued field, and CP, the completion of the algebraic closure of the field of p-Adic number, is an example of non-spherically complete non-Archimedean valued field. Let E be a non-Archimedean normed space over K. Recall that the norm defined on E is called non-Archimedean if it satisfies the strong triangle inequality. If the I is a family of subspaces of E, then the linear hull of the union of the I is denoted by such notation. We say that two subspaces of E are called orthogonal if the following equality holds. Next concept, the set of elements, non-zero elements of E is called an orthogonal base of E if the condition of orthogonality is satisfied and every X has an univocal expansion. We say that E is of countable type if it contains a countable set whose linear span is dense in E. If K is separable, then E is of countable type if and only if E is separable. Let Ti be a system of non-Archimedean Banach spaces. An orthogonal direct sum of this system is the space of all the elements of product for which limes is of norm equal to 0, normed by the maximum norm. Teres, Garcia, and Shikov introduce the concept of the orthogonal finite dimensional decomposition property in the following way. We say that a non-Archimedean Banach space E has the orthogonal finite dimensional decomposition property if E can be expressed as the orthogonal direct sum of a system of finite dimensional linear subspaces. Then, for all I, the I is orthogonal to the subspace for the remaining J's, and every X can be written as a sum where every Di is an element of Di. An orthogonal base decomposes a Banach space into a direct sum of one-dimensional subspaces. Hence, every Banach space with an orthogonal base has the orthogonal finite dimensional decomposition property. If K is spherically complete, then every finite dimensional space has an orthogonal base. Hence, E has the orthogonal finite dimensional decomposition property if and only if E has an orthogonal base. So, if K is spherically complete, then the class of Banach spaces with the orthogonal finite dimensional decomposition property is equal to the class of Banach spaces with an orthogonal base. If K is not spherically complete, there exist various kinds of finite dimensional spaces without orthogonal base. From this K, the class of non-Archimedean Banach spaces with the orthogonal finite-dimensional decomposition property can be proved as a natural proper generalization of the class of Banach spaces with an orthogonal base. Perhaps it is worthwhile to show at least one example of a Banach space with orthogonal finite-dimensional decomposition property having no orthogonal base. Let K be non-strictly complete. Then we can select a nested sequence of closed balls in K with an empty intersection. And now, using the construction presented by Van Roy in his monography, we can define a non-Archimedean norm on the product of two copies of K. This normed space has no orthogonal base. And then we can construct this space of Hunter-Gu type as a direct sum of this space and C0. And this space has the orthogonal finite-dimensional decomposition property, but it has no orthogonal base as this space. This subspace of this space has no orthogonal base. It is worthwhile to remark that Wiesław Śliwa, studying a non-Archimedean Frechet spaces, constructed a non-Archimedean Frechet space of Hunter-Gu type without a Schauder basis, but having a finite-dimensional Schauder decomposition. Perez, Garcia, and Shikov introduced the property, the orthogonal finite-dimensional decomposition property, studying approximation properties. Recall that a non-Archimedean normal space E has the metric approximation property if the identity on E can be approximated pointwise by final rank operators on norm 1. And they proved that a non-Archimedean Banach space with the orthogonal finite-dimensional decomposition property has the metric approximation property. The idea of this proof is quite simple. First, they prove that the direct sum of the system of non-Archimedean Banach spaces has the metric approximation property if and only if each component has the metric approximation property. Clearly, finite-dimensional spaces trivial have the metric approximation property, hence the conclusion follows. They observed that the converse of this implication is not true, and they pointed out one example which I used in different contexts, an example of a closed linear subspace of L infinity over not strictly complete K, having the metric approximation property, but not the orthogonal finite-dimensional decomposition property. Under additional condition, Perez, Garcia, and Shikov proved that a non-Archimedean Banach space of Hunter-Gu type has the metric approximation property if and only if it has the orthogonal finite-dimensional decomposition property. And they formulated the following problem. Is the orthogonal finite-dimensional decomposition property hereditary to linear subspace? And they presented a counter answer. Let E be a non-Archimedean Banach space with the orthogonal finite-dimensional decomposition property, and D be its linear subspace. And for such notation, they prove that D has the orthogonal finite-dimensional decomposition property if D is finite-dimensional, or D is orthocomplemented in E, or D is dense in E. We found another partial solution proving such theorem, assuming that a non-Archimedean Banach space can be decomposed can be expressed as a direct sum of two closed subspaces such that one of them has an orthogonal base. Then we prove that every finite codimensional subspace of E has the orthogonal finite dimensional decomposition property. We suppose that there is a negative solution of this problem, that there is a possible to find an example of a Banach space with the orthogonal finite dimensional decomposition property having a linear subspace without the orthogonal finite dimensional decomposition property. And we are looking for pathological properties of non-strictly complete valued field, which can be helpful for such construction. And we let K be non-strictly complete, non-Archimedean valued field. By K with head, we will denote the spherical completion of K. This is a valued non-Archimedean valued field, which is spherically complete, but we can consider also the space as a Banach space over K with the norm given by its valuation. And there is no non-zero element of K with head that is orthogonal to K. And we choose infinitely many elements of K with head outside K. By K, I mean a one-dimensional linear subspace of K with head generated by 1, with the norm equal to 1 and equally away from K. And we can recall that this distance is not attained. And next, we set the set lambda big, which contains the selected sequence of lambda E, and considering the space of all bounded sequences of elements of K with head, we construct a closed linear subspace of this space with the restricted subnorm where E1, E2, and so on are the usual unit vectors of Kn. And this Banach space is a K-Banach space of Kontevou type, and it has the orthogonal finite dimensional decomposition property, as P lambda can be expressed as the direct sum of two-dimensional linear subspace dk. And next, defining two orthogonal sets. The first one is the set of unit vectors, and the second one is the set of sums of unit vectors multiplied by lambda, and then we define the linear subspace d lambda, the subspace of E lambda, as a closed linear subspace generated by this set. Then d lambda is a one-dimensional subspace of E lambda, since E lambda can be expressed as a sum of d lambda plus the one-dimensional linear subspace generated by lambda 1 multiplied by E1. For such lambda, we define the relation on lambda by the following formula. Two elements are in relation if we can find such scalars for which a lambda I plus b belongs to the ball in K with head centered by lambda j. And for such notation, we prove the following theorem. D lambda has the orthogonal finite dimensional decomposition property if and only if lambda, the set lambda, has finitely many equivalence classes with respect to such defined relation. And the second point of this theorem, taking K equal to the CP, the completion of the algebraic closure of the field p-Adic number, we can find two infinite sets, lambda 1 and lambda 2, such that for the space T lambda 1 generated by the set lambda 1 and its linear subspace d lambda 1, we prove that d lambda 1 has the orthogonal finite dimensional decomposition property, and for the second lambda 2, there is the closed linear substrate d lambda 2, which has not the orthogonal finite dimensional decomposition property. In other words, the set lambda 1 is selected in such a way that it has finitely many equivalence classes with respect to the relation, and the second set has infinitely many equivalence classes with respect to this relation. So finally, the list of references which I use in this talk. The first group, the references related to the classical results, and the second group of non-Archimedean results. And in conclusion, I'd like to leave for reflection two queries. The first one about other possible applications of orthogonal finite dimensional decomposition of non-Archimedean Banach spaces, and the second about further partial affirmative solutions of the problem: is the orthogonal finite dimensional decomposition property stable for linear subspace? So I asked about possible assumption for which the orthogonal finite dimensional decomposition property would be stable for linear subspaces. So thank you very much for the attention.
Okay, thank you, Albert. Any questions? Any comments? Okay. All right. Then we thank Albert again.
Thank you.